sign of this constant, as this is the sign of that k number, which tells you if you're in a sphere, you will collapse. If in a hyperbola, you expand forever. If you're flat, you're marginally bound. So marginally bound is a constante contorno. Como é que é? Contorno? No, it's not contour condition. Boundary condition. Yeah. So this has this special boundary condition that at infinity you arrive with zero speed. You have exactly the amount of energy to escape. And that seems fine-tuning, and I'm not explaining I'm not so why it's fine-tuning, but I'm telling you that so you can appreciate the power of inflation once you start studying cosmology in a longer course. Okay, so that was the first freedom equation. There's another freedom equation, it's called the second freedom equation, and that tells about the acceleration of this scale factor. That's the one that it's kind of interesting. And because it's GR, every property of matter in GR creates gravity. In Newtonian physics, only mass creates gravity. In GR, the entire energy momentum tensor creates gravity. So if you have pressure, you have gravity. If you have heat transfer, you have gravity. If you have anisotropic stress, which is this anisotropic moments that you learn in classical mechanics too, you have gravity. So in particular, for the acceleration of the scale factor, which is gravity, it's a curved space-time, it depends not only on the density of matter, but also its pressure. You can see that, this is negative, so if this is positive, this is a negative, the universe decelerates, like in our sphere. It can collapse, it can expand forever, but it's always decelerating. It's never accelerating, because gravity is the only force. Gravity is pushing things together in the sphere, so, the acceleration is always negative. But GR does not imply gravity is always attractive. That's some bizarre properties of GR. Gravity can change its signs as it happened to EM, as it happened to the electrical field. But to do that, you need some negative pressure. You actually need the pressure to be lower than -ρ/3. And then you start to freak out because you ask yourself, what the hell is negative pressure? We don't see negative pressure in our daily lives often, but it actually exists, and in the WhatsApp or after this time I can talk about historical examples of a negative pressure in fluids that was actually a huge problem in the Navy of the United States. It's a metastable, but I can talk about it. But what negative pressure means is that usually if it's pressure is positive and you have this gas and you try to collapse the gas will fight. The gas will try to hold together. And that's stars. Stars is just gas desperately trying to hold together, under its own pressure. Negative pressure is the opposite. You try to expand something and then it holds you tight, like a rubber. Okay, so that will be what negative pressure is. So you need negative pressure, and that's exactly what dark energy and the cosmological constant gives to you, and we can talk about that later. Well, so this is the equation. There's also an interpretation for that equation. And it's based on one of the most important formulas you learn in classical mechanics, which is the Poisson equation. The Poisson equation is the Newtonian analogous of how matter creates gravity. Matter creates gravity through the gravitational potential. Spatial variations of the gravitational potential tells how matter moves, and the cycle continues. It's a yin-yang. And so if you do, this is the Poisson equation, and then you have to take the dust off of your mathematical physics book or the lectures if you have, or the notes if you haven't burned them. And to remember that, in spherical coordinates, that's the way you calculate a Laplacian. And, please hold tight, Laplacians are cool. So you have this, it's not, in spherical coordinates, Laplacian is not just the second derivative of the radius, there's this extra factor. So, so let's try to solve this equation for the same sphere of dust. And if you do this, so basically, let's do this, more or less by heart. So you have r squared here, you just multiply. The integral of r squared is r cubed over 3. So that you have an r cubed over 3 here, exactly the 3 here. And then you have an r squared that you divide, so in the end you get 3 and you get an r. You lose 2 powers of r. Okay, so that's basically what this equation tells you. And remember, the cycle is matter creates gravity to the Poisson equation. Spatial variations of this potential creates an acceleration. That's the cycle. So if you write the acceleration as minus the gradient of psi, and you remind that you got an x effect of r here, because you remind that m over r cubed is rho, you kind of recover the Newtonian analogs of the second Friedmann equation. So even though it's gr, at least in this special case, it has an intuition that's very solid and very grounded in Newtonian physics. One tells how the sphere, the energy of this, what's the energy of this sphere? Will the sphere recollapse or will expand forever? The other one tells how the acceleration of that sphere, expanding sphere behaves in time. The only difference is that you got this 3p in the equation that doesn't exist in Newtonian physics, and that's because in GR, every property of the energy momentum tensor, or the stress, in classical mechanics, you learn it as a stress tensor. Every moment in the stress tensor, every component in that matrix creates gravity in GR. In particular, you got this extra term. Questions? Are you okay with this sphere? It's very important that you understand this spherical model, because that's the intuition that we build. We don't have an intuition GR, so build your intuition in Newtonian physics when it's appropriate to do so. Are you okay? Are you hanging tight? Okay. Ask me questions. Good. So there's a third equation, but the third equation, it's not an independent equation. So that's in the homework. If you play with the first and the second Friedmann equation, you can actually derive a conservation equation for the matter itself. And that's the conservation equation. You can see that it's how the derivative of the density depends on the scale factor. And it has this simple form here. So, you know, this me? Okay. D log rho dt plus 3 d log a. So this is basically the Hubble function. 1 plus w equals 0. And this is w is just a definition, is the sum of the pressure divided by the sum of the densities. And if the different components don't interact with each other, you can actually put w for each of the species itself. So you probably heard about it, like cosmological constant has w equals minus 1. Dark matter has w equals 0. Radiation has w equals a third. The cosmologists love to talk about this. And you ask, what the hell is w? This is w. It's just the fraction of pressure to a higher w, a w that has a module that is greater than 0 means that pressure is also contributing to gravity. Okay. So let's do some more examples. So you have dark matter, which is basically non-relativistic matter. Non-relativistic, the density is just the mass of each particle times the number density of particles. So non-relativistic matter is matter where the kinetic energy doesn't contribute to your total energy, because there's a c² factor there. So W equals 0. Relativistic, you have actually W equals a third, and to show this, you remind that in relativistic, the density of relativistic, you have the number density of photons, and that just decreases with the cube of the radius. Now, as your sphere expands, your density of photons decreases the cube of the radius. But remember that photons also redshifts. We talked about this last class, and that gives an extra factor. So rho actually decays at 8 to the minus 4, and then if you solve this equation, impose that rho decays at 8 to the minus 4, you get W equals a third. Curvature, if you do this for curvature, you actually get W equals minus a third, and the cosmological constant has W equals minus 1. These simple examples, they have constant equations of state. That's usually what you start with in cosmology course. But that doesn't have to be the case, and I have done work in species that you don't have a constant equation of state. So you want to solve this equation, assuming that this depends on time, and as an exercise that the solution of this equation is given by this integral. It's exponential of of an integral. And I will give you an example of something that's important for cosmology that doesn't have a constant equation of state, which is massive neutrinos. Massive neutrinos is pretty hard. Massive neutrinos is the exoplanets of cosmology. Okay, it's pretty hard. Everyone wants to work with. My last paper in March was about it, so you know. So and the interesting of massive neutrinos is that they have mass, and in the early universe they were relativistic, so they have a W equals 1/3. But as the universe cools down, they became non-relativistic, W equals 0. So it's basically W equals 1/3, W equals 0, and there's a transition between them. And massive neutrino is the revenge of cosmology against particle physics. So particle physics in the past used to tell that cosmology is like philosophy. We couldn't prove anything, there was no data, and that was true like in the 1930s, 1940s. But now we have so much data that we can prove properties of particles better than they can do, and the absolute scale of the mass of neutrinos is something that cosmology have to answer. Okay. So are you okay with that? Is everyone on board? Come on, ask me questions. You did last time. Because now, if you understand, now I'm going to talk the biggest mistake. Einstein was so smart that his biggest mistake was actually awesome, and it's the cosmological constant that explains everything. So I will explain like his biggest. And when you read about it, he was very depressed. You say, oh yeah, he did 2 + 2 = 5. No, that he didn't. That's so. What happened is that Einstein believed the universe was static. The universe, doesn't expand, doesn't change in time. It always looks the same. We know that a static universe has the problem of having too many stars. That's the Ober paradox. He just ignored that because the other Ober paradox existed at that time. So, and you know that equations from his own theory predicts scale factor that usually is not a constant, a scale, it produces a dynamic universe. Most of the solutions in GR are dynamic universe, and he hated that. He said that God would not create something, that is changed with time, and why? But so he tried to put by hand something that will make the universe static. So that's why he created the cosmological constant, and so I want you to understand how you do that. It's actually not very complicated. So you have the Hubble function, which is the first derivative of a scale factor, and you have the second freedom equation, which is the second one. So if the universe is static, this both needs to sum up to 0. Okay, you need the velocity and the acceleration to be 0, so the scale factor doesn't change in time. Okay. So to this to be 0, you need this requirement for, you need the sums of densities to be minus the curvature. And you need this guy to have an equation of state of minus 1/3. Okay? We know that if the universe was empty, curvature has an equation of state of minus 1/3. So if the universe was made of ghosts, that would be a solution. But we know we exist. At least we think #matrix. So in that one, there is dynamics, there is the scale effect. So how you put it? So that's how he added cosmological constant. So he added his extra density such that this sum will be minus rho k, and this sum here will have a W equals minus 1/3. So matter doesn't have pressure because it's non-relativistic matter. So the sum of density will be minus 3 times the pressure of lambda. Okay? And you can solve these and you can get this ratio here. And you can see there's a very fine-tuned constellation between lambda and k and lambda and matter. Okay? It works. The background. But we know the universe is not homogeneous. We know that there is voids, there is clusters of galaxies. So, and we know the cosmological constant is a constant by name. It's the same everywhere. So you can see here that this is an unstable solution. Whenever you get a solution of a differential equation, you have to perturb this solution to see if it's stable against small oscillations. Because there's, small oscillations in your system happens all the time. And so when you do this, you see that this is an unstable universe. And that's why he called it a mistake. It's a pretty fucking smart mistake, but it's not 2 + 2 = 5. But now you learn how Einstein screwed it up. Okay? So the biggest mistake of my life. Questions? Is us. So when you learn, so he asked why there is no relativistic matter. So when you learn special relativity, you know kicks in when velocities are approximate the velocity of light, speed of light. So that's relativistic matter. And whenever you do special relativity, like how the energy density depends on the mass, you see that when the velocities are much smaller than the speed of light, Newtonian physics is well behaved, and that's no relativistic matter. In Newtonian physics, the density is just the mass over the volume. In relativistic, there is extra corrections, and I'm just saying that these extra corrections are negligible. Right. Because we know that light, and we know there's dark matter. And light and dark matter, they both produce gravity, and they're actually very important, equally important in the early universe. That's what I'm just putting what we actually see in the universe. We see there's light. Light is relativistic matter. Relativistic matter. We know there's dark matter and baryons is no relativistic matter. And we know there's something else, which is dark energy, and we theorize this cosmological constant. So we're just including things that we know exist. And see how that produces how this produces the universe we see. Okay? Questions? Any more questions? Okay. So that's what I have to say about the equations of dynamics in the background. And I want you to study some of the components that produce our universe. And the first one is dark matter. So let's study like how do we discover dark matter? There are multiple ways to prove dark matter. What are the properties of dark matter? And why it's so fun to study dark matter. Okay? Everyone on board? Okay? Good. So the first way to discover dark matter is to the rotation velocity of galaxies. So basically, we take a galaxy and we see how the stars rotate on galaxy, and we see how the speed of this rotation varies with radius. We know that for our solar system, where the mass of the sun is like 99.9% of the mass. We know how speed takes to get those laws, by the way. So have some respect. Speed squared divided by a cube is a constant. So if most of the matter in the galaxy is in the center, or near the center, we should expect the same behavior. But when we see we see that they have flat rotation curves. You go further away in the galaxy, and the velocity, the linear velocity, doesn't drop. Okay? And you can see this for many different types of galaxies. This is real data I took from a paper like less than 10 years ago. So you can do like centripetal force equals gravity, and say, okay, how my matter has to behave in order to get the flat rotation curve, and you get the matter should increase with the radius. As you go further away, you have more matter enclosed in the galaxy. But we don't see that. Baryonic matter that flash, doesn't behave like that. So this is the rotation of our own galaxy. That's the Milky Way. And you can see there's also a flat component. So when you take into account everything we see, we get the bulge, and we talk about the bulge in other classes here. We get the disk, plus rings is just because the disk is not solid, the disk fluctuates, and it's a detail. But basically the disk, and they go down. They all go down. They are the prediction. There's no matter in the disk. There's no matter in the bulge to produce this flat rotation curve. So you have to create something else. That's Let's just call something else dark matter, because we don't see it. This is one of my favorite examples. So I would like to have 2 more lectures because I would like to teach you recleansing. Come on, you can do Saturday here. Because recleansing, how gravity towards light depends only on the total matter. It doesn't care if the matter is visible or not. So this is a cluster that just go through each other. They love so much that they hug and they just, they go like a bullet through each other. That's called the bullet cluster. And then, and so they were like this, and they pass through each other. So red is gas. Gas has cross section. So you can see here the shock wave. Okay. Dark matter, this invisible matter, we don't know if they have. In fact, they don't. So they just pass through. So what is showing here is showing the gas, and the blue here is showing the center of mass of these clusters given by recleansing. So what we see is not the center of the mass. So what the hell is the center of the mass? What is the mass that is actually impacting the center of the mass of these clusters? It's not what we see. Like, if this is not exciting, nothing is. Like, we see something, and we see that it's like 10 times more something else. No. Okay. There's a third one that is involved, because someone told me they're suffering classical mechanics. I'm just putting classical mechanics everywhere in my lecture, If you suffer, just suffer twice, Now, I'm going to try to take you the fear of classical mechanics. There's the first I will rederive an article now from 1938 from Zicki. That was the first detection of dark matter in 1940s using classical mechanics 1. So this is something that I learned in grad school. I always thought that I would do quantum field theory in 15 dimensions with 2 strings to have some, interesting results. But you can. That's not true. You can actually use things you learn in all your undergrad courses to do groundbreaking discovery. So this is classical mechanics 1. It's a groundbreaking discovery. So basically, it tells you that you have a cluster and you have a particle here, okay? And here is the center of my axis. This is the position of the particle R, and I want you to sum the gravity that of all other particles on that particle. So this is the acceleration of this particle will be due to the gravitational force of all other particles. Gravity is a two-body interaction, so you do the interaction between particle I and J, and you sum to all the particles except itself. Okay? Then you do a dot, so then you do a trick. So this is an acceleration, so you do a dot product with R. So you do a dot product with R here. Don't point at this is just third Newton's law plus a dot product. And you rewrite this as a kinetic energy. So you rewrite this as this guy, as an acceleration plus an extra term. Because, if you want to do this versus this, you get an extra term here that you have to cancel. So I'll write this as an acceleration. Now I have gravity, and then I have something that you can see already that this is just the kinetic energy times Q. Kinetic energy mv squared. That's mv squared. Okay? So you just put the other side and just tell the acceleration of the and then you do something else. So this is for the particle I. Now I want to sum over the particle I again. I want to sum all the forces, and then you get that the sums of all acceleration is just 2 times the kinetic energy of the entire system plus the potential energy. Okay, so that's something you can do in classical 1. So then a cluster is created, and you wait this cluster to get into equilibrium. Equilibrium means nothing will happen anymore. The cluster will always look the same. And in particularly, in equilibrium, the average of these guys is just 0. And that's the classic and very famous theorem. Okay? So the Vivian theorem tells us that the 2 times the average of the kinetic energy of the system, potential energy is 0. Am I getting some noise? Okay. No, that's okay. I'm gonna not move. Don't move. No one moves. Okay. Okay. So So, okay, so this is the equation. This is the famous zero theorem. So let's put some data. This is observational cosmology. This is not theoretical cosmology. So we need data. So basically, in astronomy, you can only measure radial velocities because it's redshift, Doppler effect. So you can, and you want to get the dispersion of that velocity. So you can see that the three-dimensional dispersion velocity of a cluster is just 3 times the radial velocity. This is Pythagoras. You have radial, you have 2 other directions. It's just sum the squares. Okay? And then you apply this equation and you get the mass. So if you observe the dispersion, the velocity dispersion of a cluster, you can get its mass through this theorem. The mass is basically 3 times the dispersion velocity, some constant. Okay? Get data. So I actually went to these 3 papers to find data. So I found that these measurements were made. So in 1999, we measured the dispersion velocity of the comma clusters. In 1993, the distance, the size of the common cluster was measured. 2.2 megaparsec is pretty common, the size of a cluster. And there's this nature, they actually counted the size of all visible matter. So you can say, if I apply these 2 numbers here, do I get the visible matter? No, you get 500 times more. Here's 10 times more. 10 times more. Okay? So where is this matter? So gravity is telling you over and over again, to rotation velocity, to velocity dispersions, to recleansing, that there is something else. So when one experiment tells you something, you can, maybe I screwed it up. But I'm giving you many directions where galaxy is telling us that there's something we don't understand about these systems. Sure? Right?
Here. I got one.
Yeah.
In the case of the comma cluster, you are assuming that it is a cluster in equilibrium, right? If it is not, could you explain the number if it would not be an equilibrium cluster?
Yeah, then the calculation is complicated. So the way astronomers think that if it's not in equilibrium, find one that's in equilibrium. Because that's what we can calculate. So this ACO here is pretty good. And so it's an approximation you can do, but it's order of magnitude. I'm doing here order of magnitude. Factor of 2. Can be wrong by a factor of 2, but it has to be wrong by a factor of 10 to explain these numbers. Okay? I think was your question, like, what about the other technique? So now I have fixed the technique and I find the cluster. So it's the opposite of your question. Okay. So if you read this paper, which is the Zwicky paper, he actually finds, in his paper like a factor of like 500, and he used the same technique. That's how dark matter was discovered. And here is the same analytical model that what tells the mass luminosity relation of many clusters as a function of the clusters. And you can see that clusters that's more massive have even higher mass, missing mass. That's the missing mass. It's like there's 500 more mass than luminosity, what you infer from luminosity. Something mentioned. Good. And the last one, which I think is pretty cool, is strong lensing. You can also reconstruct, so there's some, it's harder to see in a projector, but it is like strong lensing, Einstein radius, all these things that you know, probably have seen. And you can use this to reconstruct the mass. And there's this frontier field. You should all Google frontier fields. It's a pretty active field of research when you take Hubble telescope, point to a few clusters, and use recleansing to reconstruct their mass, and then you got there's much more mass than visible light predicts. There's also recleansing. I can just skip this. And then this I want to talk about, because this involves a student from a Federal University of Rio Grande do Sul that's doing an amazing job in the United States. Okay, so we know there's dark matter. So there's a question we can ask. Does dark matter have cross-section, with each other? Like in the bullet cluster, they pass through each other, so the answer is probably not. But there are other ways to test if there's interaction between dark matter particles. So one interaction that this student was interested in is there friction? Friction is what makes Aquaman sucks, remember? Yeah, like friction makes you move like this, and Aquaman just moves like that in the ocean, Hate that, hate that movie. Okay, so he had this awesome idea. Suppose there is friction, and there's a big cluster here. of dark matter, and then a galaxy comes in, and a galaxy has its small halo of dark matter. When the galaxies fall, the halos will find the friction, and so the halo around the galaxy will slow it down because of friction. But baryon doesn't feel this friction. The galaxy doesn't feel the friction. So what happens is that the galaxy gets above. The galaxy goes too fast and gets above its halo. When you have a small displacement in gravity and you do perturbation theory, you get a harmonic oscillator. Everything goes into a harmonic oscillator. So the galaxy will wobble back and forth as a harmonic oscillator and will become puffed. And here, so it's a thin galaxy that wobbles around and becomes puffed. So he did an amazing work at the University of Pennsylvania to try to get the theoretical predictions. So then he fits a polynomial of these oscillations. And you do a quadratic fit, and you can see these oscillations of, this is just a quadratic fit, the quadratic coefficient, and you get these wobbling coefficients that doesn't exist in cold dark matter. And then he actually went into simulations to measure this effect. And now the Dark Energy Survey is trying to measure this and prove there are frictions between dark matter. Good balbúrdia. The type of balbúrdia that, makes the president happy. Okay. That's everything I have to talk about dark matter. Questions? I hope, so I did a concurso, which I'm not talking about the place, and one of the members was well known in the past that didn't believe in dark matter and actually didn't get the job. So I want to teach you that dark matter exists, and if you become famous and do a concurso, for a new generation, don't give them the job if they believe in dark matter. So that's I hope you now all believe that dark matter exists. Okay. Questions? Come on. Perfect time. Louder.
No. I do have one question. I don't know if you will talk about this later, but I will do this question now. There are, I know are cosmologies, right? So, but I heard there are another vision instead of dark matter that they propose theories of modified gravity.
Yeah. Okay. They exist. There's no model that is even near to explain all these problems. So that is something that you have to avoid in your scientific career. That is some physicists, if you have 5 experiments, some physicists choose 2 that fits their explanation and ignore the other 3. And so I've seen a lot of this in cosmology, and I can say by far no one explains all these different data sets, and all the models seem very contrived. Can it be? Yes. It's not what I would put my money on. Okay. So, yeah.
So thanks for the comments. Every time I teach extragalactic astronomy or cosmology, I reinforce the idea of dark matter. I don't see any discussion there, so thank you for being so emphatic on pointing it out.
But you will say that I'm emphatic about everything, so
no, but at least on this point, I certainly agree with you. My question is actually regarding the particle side of it, and this is something I don't know if you were going to comment at some point. No, or if you want to comment now.
About the particle side of it.
But it was something I've been seeing people that work on dark matter from the detection point of view is that they're getting a little scared with covering too much of the parameter space in the cross section and everything, and they're not detecting what they thought they would detect.
Cosmology is not a safe science. You have to have, it will scare you in many fronts. That's one of them. So we know there's basic non-modified gravity, but we just don't detect the particle. So yes, it's quite scary. And we are reaching the observational limits that we can do on Earth. That's good now. We just now need $1 trillion to put something on the moon. Hashtag Elon Musk. Instead of just putting things on Mars, let's put things on the moon. Yes, so it's scary, but no, we're still trying. Good. So dark energy. Now, if the last section was kind of ghostly, this one is, this one will freak you out. Okay. So how do we detect dark energy? So I will kind of revise supernova again, but in greater detail. And then I would like to spend half an hour, 20 minutes to try to teach you a good exercise. Maybe I will go a little bit over 1 hour 10, just 5 minutes. But I ask questions in the middle. So yeah. So dark energy. Let's come back to dark energy, and let's come back to the problem of supernova. Remember, measuring distance as a function of redshift is hard in cosmology. Remember, that's one of the messages of last class. So we need objects that you either know their absolutely magnitude, which is not the case of supernova, or you know how to calibrate them. If you have two supernovas, you know how one supernova is intrinsically brighter or intrinsically fainter than the other one. So you know how to calibrate relative distances. You know how supernovas at high redshift are compared to supernovas at low redshift. Okay? So that's the case. So we can calibrate intrinsic luminosity. And here is our compilations of the distance models, the difference between absolute and apparent magnitude as a function of redshift. Okay? And these are the supernovas. And the interesting thing is the following. There's a lot of dark matter, so we can create a universe that's only dark matter. Okay? Because various dark matter is basically the same for cosmology. No relativistic. If you do this and you calculate the distance, you find that the predictions of this distance is something like here. Okay? This point here at redshift 1, like here, is basically what a universe with only dark matter predicts. Yeah. So, people turn off your microphones. Yeah. Okay. So. Okay. Don't jump. I'm not jumping. No. I'm. No one moves. Okay. Okay. So, what we see here is basically that supernovas are kind of like half of magnitude fainter than they should be at redshift 1. And if you tell the supernova community that they are messing up by half a magnitude, you're going to get some enemies, okay? Because they think they can do this exercise to 0.1 magnitude, sometimes 0.1 magnitude. So supernovas are too faint. That means they are too far away. There's something that makes the universe to become bigger than it should be. And when you put this in the equation, that tells that the universe is accelerating. So that is how acceleration was discovered. Supernovas are too faint at redshift 1. Okay. But one thing that I want to emphasize that the way this measurement is done is that we have this supernova here at low redshift, these supernovas at high redshift, and we know how to make the relative luminosity between these and that. I will say this over and over again, because supernova is relative distance. Okay, so why we just don't go up to redshift 0 and just measure the Hubble constant? To do that, it's hard. Why it's hard? Because there's not enough supernova. Supernova is a rare event. So here is the fraction that's like 10 to the minus 4 supernovas per megaparsec cube. This is just 0.7 cube. So this is like 10 to the minus 4 supernova per megaparsec cube.
Eu vou gravar de novo.
Or, it could be my, Time for a burrito. Did you see what that was? Nice man. Yeah. No. Okay. No. We can survive this. Look, come on. Let's continue focus here. It's important. Okay. So we can do this following exercise. You can do it at home. So basically, a supernova field that we measure is the dark energy. So it's basically like 3 degrees square. That's like 10 to the minus 4 times the sky. And if you see the co-moving volume at the redshift 1.1 is basically a gigaparsec cube. So take the volume, and because the volume is the whole sky, times the 10 to the minus 4 and times this, and you see that you should get approximately 1 to 2 supernova per year at redshift 0.01. Okay? So there's not enough supernova to go all the way down to like solar system. And that's important because that's why in the Hubble constant exercise, we need the ladders to the supernova. We went from parallax to Cepheid until there was enough volume that we could observe a lot of supernova. Okay? Volume is everything. Okay. So, good. So, people say, so the next one is, people say, supernovas are a standard candle. You have heard this. They're actually not. They actually vary a lot. They're absolutely.
Block off.
There's a between them. Here, so this is the light curves of many supernovas that they have, and these are kind of the absolute magnitude over the Hubble constant. So this, and you can see it varies a lot. And if it varies like that, we cannot do any cosmology with this. But the elegance of supernova is that you can see here, the supernovas that are fainter, they kind of decay faster. Can you see here? You can see that there's a slope here in the decay. And that's the brilliance of supernova. Because there's this Philip relation that tells how this guy varies with respect to the decay of these guys. And when you apply this Philip relation, which is this linear relation between absolute magnitude and the decay of apparent magnitude after 15 days, you can get this dispersion to reduce to this guy. And with this, we can do cosmology. Okay? So that's why we use type 1a supernova, and we don't use type 2, type 2b. We don't use, stars, because supernovas can become well-behaved if you apply some corrections. And one of them is the Philip relation. So this is the relation here. It's pretty tight. This is the other relation. And here, this graphic, it's kind of lying to you. That's the last time I'm going to talk to you, because this is absolutely magnitude. So say, oh, Viva, then, okay, you're just wrong. You can't calibrate. But this is not actually true. This absolute magnitude here assumes a value of the Hubble constant. And if you change the value of the Hubble constant, you change this guy up and down. So what supernova tells you is the slope of this relation, but it doesn't tell you the amplitude of this relation. And that's what we need to do the Hubble constant. And that's why we need all those ladders that I told you yesterday. Okay. So supernova can be calibrated. High redshift supernova can be compared to low redshift supernova. And when you do this, you find this. So so the one that I showed before was the state of the art, okay? So this was the original 1998 discovery of dark energy. You have low Z supernova, high Z supernova. You put the distance, the prediction of a distance of different cosmology. So this cosmology has dark matter and lambda. And you see that a pure dark matter here goes like this. Half of magnitude at the redshift 1. It's a very good rule of thumb. And the supernovas are way too faint. So you need a cosmology with the cosmological constant. Einstein was so smart that his biggest mistake is like our biggest accomplishment. We showed that lambda exists. The universe is not static. His application is wrong. But it seems that lambda exists. So one thing that you can do yourself is then you can do, you can recreate a likelihood, explore the data, and get what is the probability contours of having dark matter and dark energy. So this is dark matter. This is cosmological constant. This is the omegas. Remember, omegas is density over critical density, so it's a dimensionless number. And you can see, and this will be a universe that's accelerating here, and most of the probability distribution, it's on the accelerating side. That's a Nobel Prize, okay? That was the Nobel Prize in 2011. Yeah, okay? So why now? So I finished with theory. So there's a bit statistics. Now I'm going to do this. I'm going to give you a Nobel Prize to every one of you. Okay? Because we're going to spend 20 minutes going from the tables of his paper on how to reproduce these results, and then I can give you. So when I was a teenager, it was like Prêmio Joinha, you know. So that's the kind of like the cheap versions of a Nobel Prize. So I'm going to show you that if you're in the right track, if you know the questions, you can publish a Nobel Prize paper with a mathematics that you can understand right now. Okay? And I think that's pretty powerful. You don't need quantum field theory in 500 dimensions with 2 strings to do something that it's a Nobel Prize level. And this is what we're going to do now. Okay, so these are the tables. This is his, go to his papers, the tables of supernova. Redshift, modulus distance, okay? The difference between absolute and apparent and absolute magnitude. So let's use these numbers to get dark energy. There's, you know, so these are the high redshift supernovas. These are the low redshift supernovas. You cannot see here, but the Dropbox has the link, and there's enough resolution in the PDFs to see those numbers. And I want you to use those numbers, okay? I give you 2 weeks to do this exercise, you know. If you want me to, you know, be very impressed to you, get to the slides, do this exercise, and you get a recommendation letter, okay? Okay, so the first thing you have to do, you have to create a likelihood. A likelihood that will tell us what's the most probable model. So let's do Gaussian. Let's do Gaussian like the simplest of example in statistics. So if you create a Gaussian, so I create here a likelihood, a chi-square, a Gaussian chi-square, which will be the numbers of that table minus what your model predicts as a function of dark matter, dark energy, and H naught. We know how to calculate distances. There's distance, then the luminosity is distance, there's log of luminosity distance, and that's magnitude. Divide by errors, and these are the types of errors you get in supernova, okay? Here I'm just reviewing Astro 101, you know, the magnitude is log base 10 of distances. And here I'm just creating a trick that I multiply and divide by H naught, so this guy doesn't depend on H naught, and this depends on H naught. Okay? And that becomes from the fact that I told you that the value of this guy is correlated with the value of absolute magnitude. So we need to marginalize over this guy. But this is just a Gaussian likelihood. And here I'm just reminding you that the luminosity distance is 1 plus z times the co-moving distance. Okay? This is what we saw last time. Are you on board? Okay? Don't panic. Okay? Stay with me. So just revise. So this is just for you when you do your homework. You know, is just revise what is the formula. This SK looks scary, but remember, it's just a sine if it's a sphere, it's a sinh if it's a hyperbola, and it's just itself. It's a plane. We proved this last time. Remember, we took a sphere, and you see what's the angular diameter distance. It was the sine of the radial distance, which is the moving one. And we are considering a model with dark energy. Cosmological constant doesn't involve redshift. Dark matter, you can prove that it evolves with the cube because W equals 0 and curvature. Okay. Good. There's one thing that here that this is just dimensional analysis, because if you have paying attention, you say, Vivian, you drink too much last night because, you know, this is Hubble constant. So let's assume X. Hubble constant is what? Kilometers per second per megaparsec. And this is distance. Distances is like megaparsec. So there's a missing constant here, and that's because I'm assuming C equals 1 all the time. So if you do a dimensional analysis, where do I put the C? So this is a distance. You can show you really quickly that this is basically, there's a C factor that's hidden here. So when you do the actual exercise, you need to put C back and know how to go to units where C equals 1 to units where C equals like the normal values. It's an important work. Another thing that I'm giving you for this exercise is the source of this error. So this is the intrinsic one. People usually put 0.15. This is like velocity dispersion of supernova that creates an error, and I just got a slow and digital sky survey value and this formula, and that's the error you got in the table, okay? So this is like experimental physics 1. I taught experimental physics 3 when I was a master student at FRJ. This is what we're doing, the errors propagation. Okay, everyone's on board. It's okay, so it's Gaussian likelihood, error propagation. Good, are you okay? Survive, come on. Wake up. Okay, so There's one technical detail that you have to do, that you have to marginalize this likelihood over the H naught, because we cannot measure H naught. So how do you marginalize a value? So you have a probability distribution that depends on two parameters, A and B, and you want to marginalize over A. How do you do this? You just integrate. Okay? So basically we are working this chi-square marginal, which is the original chi-square, which is a Gaussian, marginalized over the values of H naught. And I put it this way because it's just easier to do the integration this way. Okay? Now it's calculus 1. I hope you had good grades in calculus 1. If you don't, there's always time to recover. Okay. So another trick is that you have the mu that depends on H naught, and you can sum and subtract the 70 kilometers per second per megaparsec. So this new mu assumes a value. That's what people do in those plots of absolute magnitude. They assume H naught equals 70. And you can make this definition. Mu, assume H naught equals 70, and you put a fancy hat here. The new data minus model, and the new chi-square with this hat. And you have this extra constant here. Okay? So now you have to do this integration. You have to do this guy. Okay? You're a student. You do by hand. I'm old lady. I do in Mathematica. Okay? So Mathematics is the most important. 10 minutes. Yes, 10 minutes, okay. We can do a universe in 10 minutes. So if you do this integral, you basically will have, if you write the variables correctly, okay, just do this, you get this integral here. I want you to do this integral by hand, be brave. I know, I just put in Mathematica because I'm lazy. But if you do this integral, you just get this value here with some constant, and you got your chi-square is actually slightly different than the original one. So basically, the chi-square that you use is the one that I showed, the Gaussian one, plus these extra terms. Okay. The next time is prior. So what's your prior? Like where you're going to do your primary values. So it's omega meta and omega lambda. So we are just assuming flat. We will assume that the prior distribution, the prior is your belief before the experiment, is that they all have to be between 0 and 1. Okay? So we have a likelihood, we have a prior, now we know how to do these contours. And that's what the Markov chain Monte Carlo simulation is doing. Because one thing you can do in this exercise, and I will give you full grade if you do, you can just grid in lambda, grid in matter, calculate the values of each of likelihood and do this brute force. That works in 2 dimensions, but doesn't work in 10 dimensions. Like I deal with problems in 50 dimensions. So that doesn't work because if you put 10 points here, that's 10, 100, 1,000, and you go over to really crazy numbers. Okay? Are you okay with this? Like if you're exhausted, I can finish here. If I can teach you a little bit about Markov chains, Monte Carlo simulations. So you can decide. All right, are you okay? Can you survive 10 minutes? Okay? So how do you do this? This is what's called Markov chains. And you are going to use, if you do exoplanets, you do Markov chains. If you do, what do you do? Yes, you do Markov chains. Markov chains you do all the time. So basically you have your likelihood that we derive, we have a prior, and we want to calculate the posterior. You want to invert this guy. First you have to use Bayesian theorem that, to invert this guy, and you get the probability of these guys given the data. So that's the first concept. And you need to sample this guy, and we're going to sample using the concept of statistical equilibrium, which is the concept of Markov chain. And the key point of a statistical equilibrium that if you choose the probabilities well and you sample them correctly, you call something that's called detail balance. So I want you to, as a homework, to go to Wikipedia and Google Markov chain Monte Carlo simulation. It will be like a great explanation of this. And so basically, the points, the idea of Markov chain is that if you're a point in parameter space, like if you're a universe that has no dark energy, omega lambda equals 0, and omega matter equals 1, and I want to transition to another universe which has, for example, no dark matter, going back and forth has the same kind of probabilities, okay? So this is the key of Markov chains. So I'm going to write this transition probability between 2 universes as my prior one, the probability to arrive there, times the transition probability. You propagate this guy, Okay, so that's kind of a homework. Then you kind of marginalize over. You can do this trick, knowing that this guy is normalized, and you get this guy here. Okay? So basically it tells you that if you choose a transition probability well between two universes, your new point will have the same probability distribution of your old point. And knowing this, that's the components of a metropolis Hastings. That's something you also need to go. I want you to go to Wikipedia and say, what is metropolis Hastings? Who knows metropolis Hastings here? You know, tell your friends, you have more time, I only have 10 minutes. Go to WhatsApp and say, this is what I learned about metropolis Hastings, give you links, okay? And metropolis Hastings is just a trick to do how to do acceptance versus probability and tells you that here. So basically, that's the last thing I'm gonna talk. So can you, go the lights, I need lights. So basically you have a formula, so that you have omega matter, you have omega lambda, and for every point of this guy, you can calculate the posterior of having them given data. You know how to do this. So basically, one thing you can do, you can grid. That is the brute force. And you calculate the posterior of every point in this grid. That's what I say, don't do that. The other one, you can do the following. You go to this point. Let's do this in red. And then I finish this talk. You do this red. You calculate, so, because you have to code this. I want you to code metropolis Hastings yourself. It's 5 lines of code. Go to this point. Let's assume that this is omega lambda equals 0.5 and omega matter equals 0.5. Okay? Choose a new universe. Choose a new universe. Give me 2 numbers of omega lambda and omega matter. Come on. I have 5 minutes. Okay, so 0.1 and 0.9. Okay, so that's a proposal. Then you ask the following. Is this point more probable than this one? Does it have higher likelihood? Lower chi-square? If it's yes, you save that point. Okay? If it's no, you gamble. Gamble is the following. Take the ratio of the likelihood of your point, your new point, divide by the old one. Actually, you have to take the log here. And that's your game. You take this ratio, which is this guy here, your universe, the pink universe, mine is the blue universe. It's less probable, okay? And then you go to your Python random number generator and choose a number between 0 and 1. Any number, just choose, okay? If this ratio is greater than the number you chose, you pick this number. If it's not, you reject it, and you try again. Okay? That is the concept of and if you do this, then you start giving me like, what is the point? So if I accept it, I have 2 points. I start again from this point to a new universe, this one. If you reject it, I come back. And you do this over and over again, and you start populating your points with the most probable, with points that we're gonna accept it. And then in the end, if you take like ellipses with like constant density of points, you get exactly what the posterior. But now you don't have to have 10 points in each dimension. The number of points you need scale linearly, not exponentially, with the dimension. So okay, so what is your exercise? And I finish this talk. Yes, it's 1. Get the likelihood, get the tables, write down the likelihood so you can calculate the posterior of one universe. I gave you the steps. Second, research what a MCMC is, research what a metropolis Hastings is, and code yourself. It's easy. If you Google Python code for metropolis Hastings, you get the answer, okay? But try to do yourself. Try to do this, Third, I want you to run the MCMC and recover those posteriors. And I will tell you later how you can plot. There's extra material here that I won't present today that you tell how to plot and how to code. There's material that I'm putting in the WhatsApp. In 2 to 4 weeks, give me back those posteriors, and you get a recommendation letter when you need a PhD. Okay, that's you have discovered dark energy. So this is the circle that I showed you in the first slide, that you need physics. We talk a lot about physics, Newtonian Poisson equation. You need the statistics. We talk about Monte Carlo, Metropolis Haiti, and you need coding. You have to do this in Python or in Mathematica or in Fortran. I code in Fortran. That's signature. Look his face like, oh, ew, you know. It's like, ew, disgusting, you know. Yeah, you can do it in Python. There's no problem. I have done in Mathematica this exercise because I love Mathematica. And get these contours. You will be so proud that you just have derived the paper that gave the Nobel Prize of 2011 with physics that you know. And the first time I did that, like when I entered the University of Chicago, the first class I took was the Science of Dark Energy Survey that was taught by Joshua Freemer. The first exercise of this course was this. I'm just repeating. Like the level of education I got at the University of Chicago is the level of education we're getting right now, because the same exercise. But that I had a grade, because you have to do this in 1 week, and it was a grade between 0 and 10. So I'm giving you 2 to 3 weeks, and there's no grading. It's just my respect, which is, come on. Okay? Good. So I end for here. That was a technical talk. The talks are becoming, you know, I try to cheer you up, but cosmology is a technical science, and please, try to do this exercise. You don't have to do it and then send me. So I'm stuck here. I can read your code. I can say, oh yeah, your MCMC is not working because of this and that. We can discuss. I will be open to that. That's finished now.
First of all, thank you for the lecture. And my question is it possible to detect dark matter with gravitational waves? And if so, what kinds of new information could it bring to the table? What could gravitational waves tell about dark matter?
Actually, one thing that gravitational waves can measure is the value of the Hubble constant, okay? If that depends on the so gravitational waves are, yeah, good question. I don't know if you can tell about dark matter. You can tell about the value of the Hubble constant, and I will show you in the lecture 4. I actually don't know if you can tell about dark matter. Good question, I don't know.
Thank you.
It's okay to say when you don't know things, okay? So don't. Come on, no question means. So yeah, so just before I just saying there is more. This will be in the zap. So yeah, so for example, I just say so there's there's some technical aspects here, things like burning. You know all about this burning, and then how to this is like a simulation how it would work. Just say this is exactly what I did. This fancy, okay, and then you can see that things are getting the distribution when you apply this, and you get the posteriors. Then how to end MCMC, and then this is actually my program, and how to plot it. So this is what I want you to show, to plot it. And I had look, I can do Python. Okay, I'm not that old. So this is a Python script that how to plot those chains and how to save them. Okay, I put this for the WhatsApp. I didn't put this for the lecture. How to save the chain so my program can read it, and I'm pretty sure you can recover this. God, please try to do it. It's so exciting. Okay, sorry, your question.
Can you back in that figure of the neutrinos in the beginning?
Yeah. Okay.
Really in the beginning.
Wait, we got there. Okay, here.
Is that some kind of bound of neutrinos? Or just oscillation?
No, the oscillation tells that neutrinos have mass, okay? Yes. And what particle physics can give you are the relative masses between the 3 states of neutrinos. So this is quantum field theory, so basically it tells you that the eigenvectors of mass, which is quantum mass, the quantum state of quantum mass, is not the eigenvectors of quantum type of neutrinos, because you have neutrinos, tau, electron, okay? So they can tell you this delta m squares here, but there's an up and down shift. We will tell the absolute scales of these neutrinos. That's what cosmology gives to you. Today it's like is around 0.3 eV.
there is no possibility that they have a bound,
What do you mean a bound?
like
The
two,
lower bounds,
three,
but
no, 3 neutrinos, like in a bound state.
okay, like an atom. I don't think so. Well, I don't know. I'm not a particle physicist. I would be very, I would be like, wow, if that happens. No,
There's some kind of
I don't think
massive neutron, but
I
just
think
in
they're
relativistic
elemental
scale.
particles.
What?
Okay. I think they're elemental particles. No, there's just them. There's nothing else. We don't break neutrinos into subneutrinos.
But that massive neutron is just in relation with the relativistic energy of the neutrino.
Yeah, but yes, they're massive, but they're super hot. You know, today they are non-relativistic, but they have lots of kinetic energy, and that's actually something very interesting in cosmology. They are much hotter, than dark matter, but in the sense of temperature, not
Okay.
This is on YouTube. I'm gonna trend tomorrow, in YouTube. Yeah.
Just for curiosity, is there any constraint about these values, initial conditions? I don't know.
These values, there is. This is an active field. Like W first will be, so we have the dark energy survey, just their release, initial release of supernova. We have, those contours. So first, okay, I have to go a little bit. Sorry, I will get there. So these are the initial constraints of this, okay? Today we are much better. Today we are like this, like it's really smaller. W first will nail that down, W first will observe lots of supernova in the ratio between 0 and 2 to 3. And there will be a lot of statistics, systematics, and they also have LSST, which is like half of sky. They also we get a lot of supernova. We get more supernova that we can use because we need to take the spectra of supernova. But these contours would just collapse. But to collapse, so we have so much supernova that we are systematically limited. Adding more supernova doesn't decrease our errors if we don't decrease systematic limitation. Astronomy is all about systematics, but yes. So this is an act, and okay. So people say that I build satellites on this newspaper. I don't. What I do, I'm a co-I a working group of supernovas. I help them to do the simulations, cosmology simulations that will tell what is the best strategy that W1 can use to measure supernova. That's like half of my job in W1. The other half is related to weak lensing. So yeah, so it's an active field of research, and I'm heavily involved into that.
Okay, thank you.
This is the last lecture. We can stay here. I'm not Sheldon, this is my mic. No, this is my spot. Okay.
It's a simple question, curiosity. When you talked about the critical density of the universe, you're considering the dark matter also?
I consider everything. So if you sum up everything, the universe, because I will show in the lecture 4 that the CMB can tell you with great precision if the universe is curved or not curved. Okay? And when I say curvature, it's curvature of spatial slices. Remember those triangles on the first lecture, because the space-time is always curved. Okay? So the CMB can measure, and the CMB tells you E0. Okay? So I sum up everything: dark energy, dark matter, you and me, baryons, and it's exactly like the critical density, which it seems whenever you have this this coincidence, you should kind of why is a coincidence? And inflation provides a dynamical way to an attractor solution that dynamically goes to this coincidence. But yeah, I sum up everything. I would really like to talk about inflation, but that's another week. Invite me to again. Yeah, we can do Saturday, Sunday,
And tomorrow you will talk about the Hubble constant difference, or no? The measure difference.
So tomorrow I will talk about a little bit about principal components, which is some people have used here, some of the students. Just briefly, and then I'm gonna start talking about CMB. And then the last lecture is all about CMB. Like, we got an overdose of CMB, and someone will have to resuscitate you, because so it's pretty fun.
Okay, thank you.
Comments?
Yeah, not a comment, just because his question inspired me a little bit, because he asked about the Mond theory, you know. So you try, we have been trying to discuss, you know, from the historical and the philosophical point of view. You know, you mentioned many times during your talk that cosmology is now a science since the 1950 more or less, because of this observational, support, and well, we have this long discussion about what's science, about what's not science. So I think it's really important not to mention that, because we have been trying to put this, taking the historical and the philosophical issues into account, to think that the Mond, for instance, and the way that you do these measurements are important, to think about what's science, what's not science, what's the role of the theory, and also the role of the experiment.
But I think okay. Let me split your answer in two parts. I think it's pretty important. First, you can say what's science, and that's hard to trick. I can say that I only work with models that are falsifiable. I work in the negative. If your models cannot be falsifiable, I don't work with them. Okay, it doesn't matter if it fits the data. It has to be potentially not fit the data. Okay? I do think Mond is falsifiable theory. Mond is this modification of the third Newton's law. Mond is not a theory, it's just a modification of an equation. You know, there's like mass times acceleration, isn't it? Yeah, force, okay? And then now there's, Mond just put, I think it's just put some kind of minimal mass. I might be wrong here. That is, even without force, I think you got a minimal acceleration, okay? So it's mass equals force equals acceleration, much above this default acceleration. And in the Mond universe, the galaxy is empty, but when you got empty and no gravity, you got to this fundamental acceleration. But this constant is the same in every galaxy and in every mass. So first, we know that if you go far enough in that rotation curve, it decays. So it's not because it should be constant everywhere. So that's like, if you do Mond versus no Mond, that's 1, 0, no Mond. Second, clusters of galaxies behave differently if they are supermassive or not supermassive. So that's 2, 0. I'm trying to get to the 7th one, so it's 2, 0. Third is that if you want to do like things like the bullet cluster, you have to make an actual theory from Mond, like a general relativity version of Mond. It's called TeVis, Argentinian name, and it doesn't work. It doesn't work to explain the bullet cluster. So that's 3, 0. So it's fast. So I'm not telling what Mond fits. I'm telling what it doesn't fit, and that's how science works. Science works with things. No, you make a prediction, and you have, in principle, I have to say, "Ha, you are wrong," and you say yes, then move on. Okay. So it's 3, 0, and well, I have to see the order. But the clusters comes from this the velocity dispersion. So it doesn't work for the galaxies, doesn't work for the clusters, it doesn't work for the bullet cluster. So you can always make your theory more complicated with extra functions to make it work. And then there's the philosophical question. You have to stop somewhere, okay? If you start building your theory with things that makes them like epicycles, at some point you need to stop. There's no recite, like when you make a cake. To say when to stop, you determine when to stop, but it's important for you to stop. Like you have to, even if you work 5 years on a theory, 10 years on a theory, you have to psychologically be prepared to stop and move else. Otherwise, you are creating not science. You're creating a group of students, believers. You're not educating your students. You're creating a group of believers in particular theory. So that's yes. So my advisor has a talk, and he has like is a person, and he put, you know, this hat you can do with aluminum foil, aluminium, that, you know, look like that, so the electromagnetic waves from the government doesn't go to your head, you know. He put this, and for the believers they put this, so they don't hear anything that disproves their theories. So, okay.
It's just in common on that. I think it's quite interesting just to wrap it up. I don't know, but the on the Mon thing, there was actually a very interesting paper published by Brazilian authors from the Federal University in Espírito Santo. I don't know if you saw that one on nature astronomy. So it was a very good paper, very interesting, in which they were analyzing the rotation curves of galaxies on the assumption of the
I know that.
of the homogeneous scale that is needed for Mon to work. And they had this very in-depth analysis, Bayesian analysis of the rotation curves, and they didn't find that constant the constant scale needed. So that would, in essence, disprove Mon. It was an interesting paper, and the proposers of Mon said they weren't using their priors properly. They came up with some other explanation, which might be reasonable, but the whole thing about Mon has become something crazy, and the avid defenders of the Mon idea,
and let me give you a
just
personal
go on
story.
Twitter on a rant. And
let me give you a personal story. So you were a physicist. So if you're a physicist, you have to have an equation with your name. So half of my PhD was to build a set of equations of analytical solutions that I'm known of, and people when cite those analytical solutions from inflations, it's a particular model of inflation, they put my name, so it's kind of, I have my name associated with an equation, okay? It took me 3 years to get that. And Planck just proved that those models are wrong. I drink a beer, you know, I call my mom, you know, but I go over it. It doesn't work, that's great, let's move on. And you have to do this, even if you take it like 5 years. And because I'm new to, people say, oh, but Mon still works. Yeah, it works. And it's fine if you do your PhD on this. Well, at least public, I would say it's fine. But you know, then you have to stop at some point. And I don't know, I can tell you what I do in my research, but I cannot give you, because what I'm applying to Mon here might actually be wrong to all. I have made bets, say this is not gonna work, that I lost. I thought, so DS is going to gravitational waves. I thought that the DS follow-up of gravitational wave would never work. I said, this does not work. And now we have a Brazilian physicist that's quite famous, I forgot her name. She was, Marcela. Marcela made that bet, I made the bet against, and now she's famous, and you know, rightly so. So I lost that bet. So, you know, you have to, and I was wrong. And it's good. You have to learn from your mistakes. You will make wrong bets. And that's life.